Hello everyone. Today's topic is Fourier Transform. The Fourier Transform is a mathematical tool used to analyze and represent functions or signals in terms of their frequency components. It transforms a time domain signal into its frequency domain representation. In this figure, you can see some signal in blue where we plotted the amplitude of the signal with respect to the time. So we recorded the signal for 1 second. So this signal function is a function of time. At the bottom, you can see another graph where you can see the magnitude of some parameter, which is a function of frequency. So this is the Fourier transformed signal of the signal we see in this graph. For a continuous time signal f of t, the Fourier transform that is denoted by capital F of omega is defined as capital F of omega is equal to integration of f of t times exponential of minus omega t with respect to dt. This is integrated from whole time domain. Here, omega is the angular frequency and I is the imaginary unit. I is equal to square root of minus 1. If you perform the inverse Fourier transform, you can recover the original signal from the Fourier transform signal. So simple f of t is equal to 1 over 2 pi times integral f of omega exponential of I omega t with respect to dt. So here in this figure, you can see some continuous signal in blue. If we try to record this signal using some electronic device, we are not able to record whole signal as it is. Instead, we can record some samples on the signal. So we will have some discrete values for some discrete times on this time interval. And we are performing our computational operations on these finite values. So we are using discrete Fourier transform instead of Fourier transform on the continuous signal. So this is the continuous Fourier transform expression. So we are integrating over the whole time domain with respect to time. However, since now we are working with the discrete samples, which are marked in red, what we are doing is we are performing discrete Fourier transform. So instead of integration, we have this summation. In this summation, capital Xk are the Fourier components, and simple Xn denotes the values of the sample points, and K denotes the index of the Fourier component, and N is for each sample point. So K is the index of the Fourier component, and N is the index of sample. So we are performing this summation from N is equal to 0 to N minus 1. That means we have N number of samples, and we start performing this summation using from 0, start from 0, because we are indexing each sample starting from 0. Therefore, the last sample has the index of -1, N minus 1. So here K over N is corresponding to frequency of the signal, and simple N is corresponding to time t. In the summation, we have this exponential function, and let's assume that Bn is equal to 2 pi Kn over capital N. So we can write this expression as capital X K is equal to simple Xn times exponential of minus I Bn. Based on the Euler's formula, E I theta or exponential of I theta is equal to cosine theta plus I times sine theta. Here I is the imaginary unit, or it is equal to square root of -1. So here we have exponential of minus I Bn. So exponential of minus I Bn is equal to cosine of Bn minus I sine of Bn. So we can substitute exponential with this cosine and sine. So we can plug this quantity again at here for Bn, and we have this expression. So this is a complex number. We have a complex number within this summation. However, if you are performing this summation, you will find some complex number for xk, capital Xk. So it takes this form. Alpha plus I beta. Here, alpha and beta all are real values. So let's go to some example. In this example, we have a cosine signal with a frequency of 1 Hertz and amplitude of 1 in some units. We are sampling this signal with a rate of 10 Hertz. So you can see the sampled points in red. So we are indexing them as k is equal to 0, 1, 2, 3, 4, 5, 6, up to 9. So we have 10 samples on this signal. So here you can see the values of the samples. For sample 0, the value is 1. We can see it here clearly. For sample 1, the value is 0.809 and the time is 0.1 seconds. For sample 2, the time is 0.2 and the value is 0.309. So by considering this Fourier transformation expression, we can find these xk Fourier components. So we start from k is equal to 0. So we are finding x0. So we are performing this summation from n is equal to 0. So at n is equal to 0, the value is 1. And now k is equal to 0 and n is equal to 0. We plug these numbers to these cosine and sine functions, and capital N is equal to 10. And when n is equal to 1, and here always k is equal to 0, since we are finding x is capital X0, the value is 0.809. And here this is for n is equal to 3. N is equal to 2. So the value is 0.309 for simple xn. Likewise, we are performing until n is equal to 9. So by using this kind of calculation, these calculations, we can find capital X0. So here, actually, we are finding capital X at k is equal to 1. So it is x1. And again, we plug these numbers to the expression. And here n is equal to 0. N is equal to 0. And here k is equal to 1. Since we are working on this since we are working on the capital X1 component. So likewise, we can calculate the capital X1. So if you are doing the math, you will find these complex numbers for xk values. So for x0, we have 0 plus 0j. For x1, it is 5 plus 0j. For x2, 0 plus 0j. Likewise, we can find we will have the values, and you can see that most of the values are zeros. Here 0, this one is 0, 0, 0 likewise. Only x1 and x9, they are greater than 0 or non-zero components. So if you find the magnitude of complex numbers, you find these magnitudes. So how do we find the magnitude of the complex number? So if it is alpha plus I beta, this is the complex number, magnitude of the complex number is given by square root of alpha squared plus beta squared. So if we plot this, if we plot the magnitudes against the k indices, we are getting something like this. So we are finding only two peaks at k is equal to 1 and k is equal to 9. So you can see that the spectrum is periodic and it is symmetric around n is equal to k is equal to n over 2. And so this is this part is a mirror image of this. So we can use only one of these parts to analyze the frequencies. So we have this magnitude spectrum, and how do we convert these indices into the relevant frequencies? Because we need to analyze the frequencies, not the indices. So this is the formula to find the Fk frequencies. Fk is equal to k over capital N times Fs if k is less than n over 2. Otherwise, we have k minus capital N over n times Fs. So if you do this math, you will find you will actually find a graph something like this. So you will find 0, 1, 2, 3, 4, and then -1, -2, -3, and -4. Oh, other way around, sorry. So it is actually so it will be -4, -2, -3, -3, -2, and -1. So you will find a peak over here. Peak over here, and peak over here. Um, so, but what we are doing here is we shift this part of the diagram to this side. So we are having this graph where we can use only this part of this half of the spectrum to analyze the frequencies. We can use only the positive part of the frequency spectrum to analyze the frequencies. So you can see that there's a peak at 1 Hertz. So what is our signal? It is S is equal to amplitude 1 times cosine 2 pi times 1 times t. So the frequency is 1, and you can see that frequency. You can see a peak at that frequency in this magnitude spectrum over here. So in this way, we can identify the frequencies of a signal using Fourier transform. So here we can see another example. So this blue line shows some signal, and the signals is actually built using a cosine and sine wave. Cosine and sine wave. The cosine function has a frequency of 2 Hertz, and the sine function has the frequency of 1 Hertz, and the amplitude of the cosine function is 1 millimeter, and for sine function it is 2 millimeters. Sorry, it is 0.5 millimeters. And the sampling frequency for this example is 8 Hertz. So we are dividing, or sorry, we are finding these samples, or we are detecting the samples with the sampling frequency of 8 Hertz. So for this 1 second collection, we have 8 samples. So this is 0 sample, 1, 2, 3, 4, 5, 6, and 7. From So we index them from 0 to 7. So here you can see the value for each sample, and here you can see the time at these samples. So as we did before, we can perform the Fourier transform, and we can find the Fourier components in complex form using this expression. And here you can see the values for each Fourier component. And these are the K indices. And the amplitudes are given here for each complex number. So we have non-zero values at k is equal to 1 and k is equal to 2, k is equal to 1 and k is equal to 2. And again, we have non-zero values at k is equal to 6 and k is equal to 7. So if we perform the Fourier transform, we will find that, and if we convert k indices to the frequencies, we will find that there are peaks at 1 Hertz and 2 Hertz. However, in the full spectrum, we have -1, -2, -3, and so on. So there should be peaks at -1 and also -2. So this is a mirror image of that. So we have peaks at 1 Hertz and 2 Hertz. So we learned that this signal is formed using two other signals. One is a cosine signal with frequency 2 and sinusoidal signal with frequency 1 Hertz. So you can see in the frequency spectrum, we have peaks at 1 Hertz and 2 Hertz. So that's it for today. So I hope you understood the basics and application of Fourier transforms. So hope you can use this to sample the signals and find the Fourier components. Thank you.